Okay, so welcome back. So let's move to the DC analysis. In order to save time, so all I just need to do, just go to the directive here where I specify my directive. Then I don't want to do transient anymore. I comment it out, so by using the asterisk, then uncomment the DC. So again, if you want to know the syntax of the DC, I'll share this material for the user guide for ngSpice. All Spice languages are Allspice Simulator, ngSpice, HSpice, PSpice, they understand the same language. So if you know the language for ngSpice, then definitely you know for every other. So I'm just searching for the syntax. So I click chapter 15. So DC. So the syntax is .dc, the source name, the source you want to DC sweep, then the start voltage, the stop voltage, and the increment. This it's if you have a second source voltage, but we just want to sweep just one source voltage, which is just the input. I think the input voltage. So the syntax is the name of the source you want to sweep, the start voltage, stop voltage, and increment. So V2, want to sweep V2, start voltage from 0, sweep it to up to the stop voltage 3.3. For yours it will be 1.8. Then the increment, if you want it to be smooth, the smaller the increment is, the smoother the sweep. So for best graphical look, you make the sweep, the step, very small. So for mine I've used 0.01. yes, and so then you can still go ahead and plot the input and plot the output. So okay, yes, so netlist, no issue, then simulate. So you can see this is the output. So we're sweeping the inputs. So this is your transfer function. This is what is known as your transfer function from your from what you've learned in class. You know this, you remember, you're familiar with this graph, this very one, this red one. That's the transfer function for a CMOS inverter. This is how it looks like. So as the voltage is increasing, the output voltage, so when it's the input voltage is low, the output voltage is high, then till it gets to a switching voltage. Again, you get to see our switching voltage here. Gets to that point, then it switches to start becoming low. So that's the point where the inputs start becoming high, so the output starts dropping to be low. Then I just plotted the inputs, the Vin, just linearly. So but we'll just focus on this red one. That's the well-known transfer function for CMOS inverter. So from here where can we say is our switching point? So that's where approximately the input and the output are equal. The input and the output voltage are equal. So that's the point on the O plot. So is it at 1.5? No, because it does not cross. So it's about, let's say, 1.6 thereabouts. That's where it's almost like half of the O graph. So it's about this point here. So where it intersects with the x-axis, so down here, so you can see it's about 1.67 thereabouts. So that's the switching voltage. So you can confirm that using this formula. Where is it? So the switching voltage. So for Skywater, you can check the Spice the spice file to know the threshold, just to approximate the threshold, then the transconductance parameter and the sizing. We just put everything in there. I think it means we'll get approximately 1.6. so that's the switching. So let's do a little experiment, then that will be all for the DC sweep. What's the experiment? So I talked about how the VM, the switching point voltage can affect, you know, noise margin, and it can affect the shape of the output plot. So let's say and you know, we said for the best shape and the best performance, we said let K and this be equal, and the implication was that let the sizing for the PMOS be greater, should be at least twice the sizing of NMOS. So let's say now they are not equal, and let's just try to make the sizing of PMOS like lower than the sizing of NMOS. Let's see how it looks like, and we do the other way around also. So let's say, so by sizing, let's just vary only the width. So for NMOS it's 1, right? So let's try to make PMOS, let's say 0.5. Oh, that's just half of it. Let's still make it more smaller. Let's say 0.2. Then let's save. Yes, run. So let's plot. Oh, there's issue somewhere. Okay. And then did I change something else? Let me just check what I changed. Oh, I know, right? Okay. There's no matching model for this sizing I've done. I think that's the issue. Okay, let me just try to see 0.5. Okay, so I really wish you had the picture of the first shot. Maybe you can just take the video back and compare the shape. You can see this looks a little bit slimmer. It's not too outward, so it's like getting closer to, you know, to the vertical axis. So that means the switching point voltage has reduced. So for the input side, so it's about where can we cut the half of it? It's not around that point, but for the input it has switched. It's no longer as wide as it was before. So before, at least it was more than 1.5. so before it even gets to 1.5, the inverter would have switched, you know. So if we should cut it at this point, so you can see that generally, though, you won't have much room to what you would call an high input voltage, because just at 1.5, or a low input, before you had much room for low input voltage, such that before it dropped to 0, the output dropped to 0, it exceeded 1.5 at least, right? But before it even got to 1.5, it had already dropped. So if you continue doing it, you see that the graph would be approaching, the input side will be approaching 0. So the noise margin for input low would be affected. It won't be really good. It won't be robust well for the noise margin for input. So let's try to increase it far more than let's make it larger than that of not the length, the width. So for the NMOS it's 1, right? So let's make the NMOS, let's say the NMOS is 1, right? So let's make this like let's say 10 if there is a device that has such definition. Okay, so you see it gets like it's wider, so this, it takes time to switch. The switching point increased, like so it takes time before the switching happens. So unlike that one the switching was between the input switching was in between 1 and 1.5, but now it's like about 2 thereabouts. So there will not be enough room. The problem with this is that, for that means everything for the input, look at the input side. It means input side is to the right, the input side is this axis, right? So everything to the input to the left, sorry to the right of of this red line at this point where it's transitioned to 0, everything on this side about the input, it's the input I you get. And the boundaries are 3.3, so that means everything from like, let's say approximately 2 to 3.3, that's input I voltage. That's the input I. So you have less room for the input I voltage, unlike when it was around 1.5. So you see, what you call input I will be higher. So you can see how the switching voltage affects the whole shape of the output response, and how it also affects noise margin. For noise margin, don't worry, with time it will get clearer. So I think that's all for the DC sweep, and not to make the voltage too long, sorry, I said the voltage. That's what you get when you've been speaking about some using electronic terms for too long. So I'm going to stop the video here, the recording here. So yeah, thank you. So hopefully we'll then move to the layout of the inverter, so you get to see how it's being laid, and we do all those things. So for now, for the inverter, we can say we are at this point now. We've successfully done step 1 and step 2 for the inverter, step 1 and step 2 for the inverter. So the next thing is to go into step 3, that's the physical design layout. Then yeah, so or if the next video is not about the inverter layout, then we can do the design for other digital entities, like the pass gate or the transmission gates, then before move to multiplexer. But anyone, it may be the layout for the inverter that would follow. So yeah, okay, thank you, see you in the next video.